Okay, it's Chandler Klebs again, and this is part 2 of my C programming language uh, unicorn project, as I call it. And I forgot to mention the part of the reason I'm calling it the unicorn project isn't just because I like unicorns, but because uni meaning one. Um, for me, in this context, it means that I'm collecting all of my best programming functions into one project. My unicorn project it has nothing to do with the horses known as unicorns, although that's just a joke from my variable names. It actually is because I'm trying to take the best functions I've ever written, my most useful things as far as my integer sequences are concerned, and combining them into one place. So this is a way of preserving my programming. Okay, so here's the thing. So what I want to say is I have worked for years on some of these programs, trying to perfect them, just in my spare time whenever I get the spare time, which isn't very often. And I want to preserve these. I've even considered publishing a book full of these things where I explain them. I don't know if I have the skill level to do that. Plus, is it worth the effort? Would anybody care if I wrote a programming book? Because other people more qualified have done so. But anyway, I'm recording this video, these videos, and I also display screenshots of my source code to Facebook frequently. And I email the actual source code files to myself, and sometimes upload them to my Dropbox or OneDrive account. So I'm really nuts about not losing the source code. And while nobody is going to care after I die except me, I'm not going to care because I'm going to be dead. Never mind, I can't English. Okay, so anyway, yeah, so I'm the only one who cares that much about these programs I've written, but they're important to me because of all the work I put in on it. It's even more important than the work I've spent on things I've built in Minecraft. Because I've built some amazing things in Minecraft, and I back up those files very extremely as well. So anyway, I'm going to switch back to my screen. So let's see here. Okay, here's my terminal. Okay, let's see here. So I'm going to show you, I have several things going on here. So I showed you this powers of 2 program here. But next, I'm going to switch this back to 1. Because I have the difficult task of now trying to explain. Okay, yeah, it's still recording, it looks like. I think anyway. Yeah, it's recording about 3 minutes in. I'm always paranoid that it's going to stop recording or something. Okay, so now okay, let's see. I'm going to do this. I'm going to do make. And notice that it displays these powers, not these powers of 2. It displays these prime numbers. And I kid you not, that is all the prime numbers that will fit into the array. And there's several ways to change this. That's a lot. Okay, so let's go to the source code of the prime number program. This is the fast prime number generator. And this one is actually a lot smaller than my powers of 2 program. So here's what it's doing. First, it zeros all of the elements of the array. And then it displays the number 2, because everybody knows that 2 is a prime number. Then it sets x to 3, basically. And then, while that variable is less than the unicorn length, it will, basically, it will, up to unicorn length, it's going to go through this array, and I'll show you what it does. But first, instead of unicorn length, let's just change this number to 100. It's also possible to change the length of the unicorn array to 100 as well and get the same effect, but this works. So here's all the prime numbers less than 100. Okay. So basically, here's how it's going to work. What we have here is we have a case where it displays the current value, which is going to be 3 at the start. So as you see, it displays 3. But then it has a clever means of finding prime numbers. So what it does is it sets y equal to x, and then it does this really brilliant thing. And okay, so basically it will do the same thing all the way through the entire array. And what it does is it sets those elements to 1. So basically at the start, the very first iteration of this loop, it's going to set the third element 3 to 1. But then it's going to keep doing that by constantly adding x to y, so that it keeps adding 3 and adds 1. So basically this is the sieve method, or sev, or I don't know what you call it. I can't English, I can't pronounce, okay? So anyway, so basically it's crossing out all the multiples of 3. That's what it does. So I kid you not, it literally goes through the entire array and sets every composite number to 1. So that's what it does, okay? So what it does is it's setting all of the multiples of 3, it's setting all of the multiples of 3 elements to 1. That means the ones that are still 0 are the ones that are not divisible by 3. So, okay, then here's what it does. After that is done, it's done all the multiples of 3, what it's going to do is it's going to go through the entire array, and then, okay, so while the x is less than unicorn length, and, okay, yeah, and that current index of x is greater than 0, which would be 1. I could have done equals 1, but greater than 0 takes 1 less character. I don't know why I care about that taking 1 less character. That's just that. Never mind. I'm a nerd. You can't explain this. Just accept it. Okay. So anyway, so then x gets 2 added to it. So x, or unix, plus 2 each time. And the reason it's adding 2 is, remember, we don't need to check for even numbers. Prime numbers, with the exception of 2 itself, are always, all prime numbers have to be odd, because every even number is divisible by 2, and it can't be a prime number if you know what a prime number is. If you don't know what a prime number is, you probably missed school and need to go read about prime numbers on Wikipedia or something like that. Okay, anyway, so so basically it starts out by crossing out all the multiples of 3, but then since x gets 2 added to it, it's going to encounter the next odd number that is basically the element 5, okay, which is going to be 0. And why is 5 0? Very, very simply, it's going to be 0 because it was not a multiple of 3. 5 was not a multiple of 3, and it's an odd number. It's not divisible by 2. So that number is going to be 0, and because that number is 0, that means that the loop ends. It will no longer add 2. It's going to stop as soon as it hits 5. Then it's going to cancel out all of the multiples of 5 through the entire array. And then it's going to do the same thing. It's going to add 2 again to 7. 2 again to x, and it's going to become 7. So then it becomes 7 and crosses out all multiples of 7. And then what does it do? It tries to add 2 again, and it ends up being 9. But here's the thing. The loop continues and skips 9. Why does it skip 9? Because 9 was already crossed out. Because 9 was a multiple of 3. So it's going, basically, it will skip all of the composite numbers that have already been encountered. So that's why it works. So basically, the reason that it does that, it's going to skip 9 because it was divisible by 3. it's going to skip 15 because 15 was divisible by 3 as well as divisible by 5. It's going to obviously skip it's going to skip 21 because 3 times 7 is 21. So what you see is it literally skips all that. So it's actually very clever, and I can do more. I can set the number to 200, and then it's going to do all of the prime numbers, all that are less than 200. This is a brilliant system. It's one of the fastest prime number generators possible. And the reason I do this in the C programming language, although I did actually write this same thing, mostly copying some source code over into Java, and it's slower. Java is slower than C or C++, because, you know, C or C++ is usually compiled to machine code, the fastest ever. So if you want a fast prime numbers, you got to program it in C. That's my opinion. Or C++ also works, but for prime number programs, you don't need classes. You really don't. I don't use classes. I don't know how to use classes. And so, see, it displays the number. Now, you'll notice notice it displays those numbers. And, well, you probably, if you're an experienced programmer, you probably already noticed that at the beginning of the loop, it uses printf to display the Unix variable, and then a new line. So that's what it does. That is how the prime number generator works. It's a brilliant system. Now let me fix this. So yeah, so now I set it back to unicorn length. So now it's going to do the whole thing. So, but just as an experiment, just as a little experiment, I'm going to do something. Let's see where we are at in the video here. Okay, we're at about 12 minutes in. I'm going to do something. I'm going to change the size of the array to 1 million. Okay, so if the unicorn length is 1 million, now we're going to generate all of the prime numbers less than a million. We're going to do that, make, and I kid you not, it literally that fast found all the prime numbers less than a million. Now, even people who don't care about programming in general, they've got to admit that finding that many prime numbers that fast is impressive. People have written prime number generators, and I've tried many different methods. I've tried the trial division method, but I think that's slower than what I'm actually doing. Now keep in mind that this prime number method does actually require a lot of memory. Okay, so now I've just changed it to a billion. So let's see what happens. I'm pretty sure that's a billion. Yes, there is 9 zeros there. Okay, so now I'm going to redo this, and let's see how long it takes to get all the prime numbers less than a billion. Now it's compiling. Now keep in mind, you need to have close to a gigabyte of memory to do this. Now, because it's going through the entire array, you'll notice it's slower. And yes, it does start out slow, but as the numbers get larger, it takes less and less time to go through the entire array. Because remember, the array is literally a billion elements in size. I've just created a static array that's a billion elements in size. And it works because my computer actually has 4 gigabytes of memory. Really only about somewhere between 2 and 3 gigabytes of memory are actually available on my machine because Windows 10 is a real memory hog. Okay, but nonetheless, I have no trouble with a gigabyte. And a gigabyte is not entirely the same as a billion. It's slightly more. But let's never mind that. Do you see how the program is getting faster and faster? That's the beauty of my method, because a trial division program gets slower and slower because it has to constantly keep dividing by the previous prime numbers and so on. This one gets faster because as the numbers get larger, each iteration of the loop takes less time than the last. So it's literally getting faster as we speak. So, and this is just funny. It's really quite funny because as you see, we're already at like 11 billion. We're at 12 billion. So we're generating prime numbers that are bigger than 13 million at this point. Did I say million or billion? I don't know, but yeah, we're almost at 15 million. And see, it just keeps going and going. Now, as you can see, it works, but it also takes a long time. And it will eventually reach a billion, which is no trouble, but that would make the video long if I just stay here and watch it. So I'm not going to do that. What I did is I did Control-C to cancel the program. So anyway, now I'm going to go back here, and so I just set it back to its default of 65536. I like that number, and so literally it's possible, however big you can make your arrays. And if you're on a computer with like 8 gigabytes of memory, you could literally do, if you had access to all of that memory for one program, you could literally do all the primes up to like 8 billion approximately. So my prime number program is actually very impressive as far as speed goes. So I showed you in my previous video my powers of 2 function and my primes program. I feel like I just explained that pretty well. Now let me see here. My previous video is uploading. My previous video is uploading, and it's still going to take over an hour to finish uploading. So that's why I decided to get it started while I record this video. Okay, so now this is the binary counter. Now remember here, I mean, there's got to be a more convenient way to switch this, although this is proven convenient. Basically, just by changing the I variable in the main function, it will do different code based on this. So this is how I test out all my functions, and I haven't even shown you the other ones. I have other functions I haven't even done. I haven't even done 3, 4, and 5 there, and they do things. Although it's simple counting, just it counts by 1. Okay, so what we see here, this is very tricky. Notice it does the 8 bits, but just to keep it simple, I'm going to change it to 4. Okay, so here's what it does. It does binary counting up to 4 bits. Now, if you don't know what the binary counting sequence is, and what the binary numeral system is, then you probably shouldn't be watching this video. Probably, because anybody who doesn't know about the binary numeral system doesn't know much about programming. It's something that, unfortunately, a lot of programming books are not covering this topic. They're really not. But a computer science course should cover the binary numeral system, because people refer to things as 32-bit or 64-bit and stuff like that. But do people know what it means? I know what it means, but does the average layperson know what it means? No, because they're not a math nerd. And the binary numeral system, I'm not going to explain all that, but basically using powers of 2, it describes everything. So I'm just going to tell you, these numbers here literally translate to, yeah, there's 0, there's 1, and then this is 2. Why is that 2? Because the powers of 2, rather than having ones, tens, hundreds, and thousands, the place values represent 1, 2, 4, 8, 16, etc. So there's 2, and then this is 3 because it's 2 plus 1. Then here's 4. Then there's 5, and then there's, because it's 4 plus 1, and then 6, 4 plus 2, 7, 4 plus 2 plus 1, and then 8, and then 9 because it's 8 plus 1, 10 because it's 8 plus 2, 11 because it's 8 plus 2 plus 1, which is like 8 plus 3, meaning 11. Then 8 plus 4 is 12, and then adding 1 to that is 13. And then, so we have 8 plus 4, which is 12, plus the 2 makes it 14. And then with all of them, it's 15. Now, anybody who does know about the binary numeral system knows what those numbers represent. But how does my function generate those numbers? I'm going to show you. The binary counter is one of the simplest programs to write. First, I set every element to 0. It's all the bits are 0. So that's what this first loop here does. Then we're going to. No, wait a minute. I just noticed something. This function makes a big assumption. It assumes that x is going to be 0 right at the beginning, which it has been, but I made a big mistake in this. There needs to be this needs to be before here. I just noticed a mistake in my program, because obviously x has to I need to guarantee that x is 0 at the beginning of this, because, for example, if x what happened to be 2 from a previous function, for example, then it would only display some of them. Oh, that's interesting. Did I not save it? Yeah. See, that's the thing, is that, oh wait, I know what's wrong. Okay, yeah, that has to be there. But yeah, that was for the loop of making, it has to make sure every element of the array starting at element 0 is 0. So I just forgot to include that. So now here, this is the loop that determines, okay, yeah, this is what actually does the printing. And so it's very interesting how this works, because, yeah, so everything is all right there. But, for example, if it only went to while it's greater than 2, then it would not display all of them. It would not display all of them, and so it wouldn't look right. Okay, so I just noticed that one slight oversight. Because, you see, Unix, or X, we'll call it X or Unix, that's a global variable. And people say not to use global variables. They say that all the time. However, there is a reason I did that. First of all, I like the fact that this array is global, meaning all functions can access it. It's meant to be used for these specific purposes of my powers of 2 or my primes or my binary counting sequences, using each one as a decimal digit or as a binary digit, as a bit in the binary counting example. So that's important. And so the index arrays of x, y, and z, like those are global. So pretty much, with the exception of the I in the main function, which is a local variable, and then in some of the functions, like they will do certain things. But yeah, anyway, I need to go back to explaining how the rest of the binary counting program works. Let me see how I am on time here. Okay, I need to finish this video up because my mom will come home and ruin everything if she comes home and starts talking to me. And then if I don't respond, she's going to get mad at me. She does that. Okay, so that's the thing. So I'm going to quickly finish this up so I can end this video. So first it sets all of this to 0. Then it does this very particular loop. And it does this while x is less than the length, and in this case I didn't use unicorn length, I just used length because they're just a certain number, and that's used as an argument. So the length was 4 in this case, but it can be any number of bits you want to do. So at first it does this little thing where it displays every bit. That's what it does. Then it does this other loop, and this one is tricky. This one, while x is less than length and that particular bit at that index is 1, it sets it to 0, and then it goes on to the next element. It does that. So it's going to start out and it's going to find any 1 bits and set them to 0. And then after that, soon as that it encounters one that's already 0, the loop ends and it sets that to 1. So here's what's interesting is, notice that I set x to 0 at the beginning, and then the loop continues until x equals that length. So here's the reason it works. So Okay, so let's just set, for an example, let's just set this to 6. So let's just set to 6, so we got 6 bits. So it starts at 0 and it does this and it counts all the way to 6 bits. Now here's what you're going to notice. The x variable, it never reaches through this loop, it never reaches the number 6. It's interesting because it will just quit as soon as it finds a 0 and then set that ultimate to 1. So then here's what happens. As soon as every single one of these are 1, then it will keep continuing and x will only increase to 6 at that point. So basically this is a brilliantly done program, because what will happen is the loop will end. This main loop is going to end as soon as x reaches that. So that only happens if all the bits are already 1 and it becomes the exact number of length. Oh, man, that was a mouthful. So yeah, basically that's it. So, and I'll just do a quick speed test before I end this program. I'm going to set the bits to 16, and then I'm going to recompile and run this program. And you see that? It literally displayed every 16-bit integer in binary. Fastest binary counter program I've ever written. It's extremely fast, it's extremely efficient, and the source code is actually pretty small. So you see that was actually a very small program. I could have made it look even smaller by removing some new lines and crunching the code together, but that would make it look ugly. And the prize program was also relatively small. It was not that big. And then the Powers of 2 program, well, it was a little bit more in depth what I had to do, because I not only had to display things, but I had to carefully keep track of the carry variable and the math and all that. So yeah, but those 3 functions, the Powers of 2 program, which I showed off in my last video, and the prime function, and then the binary counter function, those are my main 3 programs, and I am going to preserve these programs or functions as long as I live. Okay, so I've done numerous screenshots. I have done, and I'm recording this video so people can literally, just from this video alone, people can type the exact source code as they see it. You don't need to while I'm alive. You only need to do that after I'm dead and you have no other way to access this code. But you can literally retype the entire source code yourself if you want. Or if you want to be really clever and do things the smart official programmer way, you would use local variables. You probably would not be using these variables. You can totally do it without using global variables. You can use local variables, and that's totally fine. I just have a preference for global variables, so I don't have to, in each individual function, define the integers, x, y, and z, or define a new array or pointer every single time in every single function. So I'm a big fan of global variables, and as you've seen, I know enough computer programming to get this stuff running. So I'm going to exit my terminal. And let's see here. So there's that. I didn't make any major changes to the source code. I mostly left things the way they were. So I don't need to make any more backups. But anyway, so yeah, that's the thing is I hope that somebody has enjoyed my programming rants, showing off my incredible C programming language functions. I really do like programming, and I'm constantly trying to think of what will my next function be. Because I'm good at powers of 2, I'm good with prime numbers, I'm good at binary counting. In the past, I've written a Fibonacci sequence program, but I just don't know which one I want to do next. And if anybody who watches my channel, it happens to be a programming nerd, if you would like to see a particular integer sequence, and you would like to see me do that, write a program that does that so I can show you, so that you can learn perhaps how it works, I can totally do that. I don't have very much time, but if I do get time and I have any requests for a future programming video, I'll probably do that. So anyway, that's all I have to say for now, and I have other things I have to do today, but I really, while I had a day off and my mom was out of the house, I really wanted to work on my computer programming, and mostly I was just showing you what I've already worked on, because I actually worked on this for a long time. I've been working on this, well, for years, but I only started collecting these things back in May of 2018, which was only 2 months ago. So anyway, I better shut up now. So anyway, hope you enjoy this video. Bye.